Hello everyone, I am Akhilesh Kumar Srivastav from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we have discussed on the last turn about the processes, different states where a process can reside in, and some processes types, for example, IO bound processes and the CPU bound processes. In today's lecture, we will discuss about the various types of the queues, different types of schedulers. We will also discuss about the CPU scheduling criteria, the different parameters related to the CPU scheduling. So, the outline of the lecture would be, we will first discuss about the process, we will take a recap of the study of the process that we did in the last turn, the process control block, we will discuss about the different types of queues, then the schedulers, then we will discuss about the scheduling criteria, and then we will try to see that how many processes can be brought into the main memory simultaneously. Now, let us have a look at the process. Now, on the last time I told you that a process is an active entity, a program is a passive entity and a process is the active entity. During the compilation process, a program gets converted into the object file, and in the state of the static linking, we convert the object file to the exe file. So, my program was, let us say, p.c, that has got converted to the p.o, the object file, at the time of the compilation or during the process of the compilation, and in the next step the files which are related to this file for the execution, their object files and the object file of this file are linked together. We call that the static linking, and during the process of the static linking the executable file is created. This executable file is there in the hard disk. Even till now this file is the passive entity, and when we bring this file to the main memory, then we will say that this has become the process. So, the moment the executable file is loaded in the main memory, we say that it has become the process. There are several components of the process when a process is brought to the main memory. The components includes the text segment, meaning that the actual code or the line of the code or the instructions, these are in the text segment of the process. There are some information related to the current execution of the program, meaning, for example, which is the currently running statement and what is the next statement to be executed. So, this is stored in the registers known as program counter, and the value of the program counter is also there as a component in the program, in the process. In the program, you may use some static or the global variables. So, all the global and the static variables are given the space in the data section. You may need the dynamically allocated memory, for example, through the malloc function, you may need to allocate the memory. So, that is the space, and the space allocated for the dynamic allocations or the dynamic variables or the dynamically allocated memory is the heap one. You may use several functions in your program. For every function call, the activation records are made, and those activation records are kept in the stack segment of the process. So, for every process we are actually allocating some space. For example, this one, we allocate the space in the main memory, we define the range in which, or the range of the addresses wherein this process will reside in the main memory. So, there is a lower address is specified and the higher address is specified. The area between two, or the lower address and higher address, area between the lower address and the higher address is known as the process boundary. In this process boundary, there are several things stored. As I already told you, the text segment that stores the actual code or the instruction, the data segment that stores the dynamically the global variables and the static variables, not the dynamic, global variable and the static variables, the space for these two. The heap region that stores the memory for, or the space for dynamic variables or dynamically allocated memories. And then we have the stack which stores the activation records of called functions. I also told you that the activation records contain various elements. For example, it contains the return address, it contains the space for actual argument, it contains the space for formal arguments, it contains the space for local variables, it contains the space for return address. So, altogether we call this the activation record, and the activation record is stored in the stack region for every function call. Now, let us look at the process states. We also discussed about this on the last turn. A process can be there in different states. We have discussed about this diagram through which we understood that what is the state of the process currently and where it can move. For example, if a process is new, the process is submitted to the main memory for the execution at the CPU. So, when the process is brought to the main memory, the process is there in the ready state. So, we are maintaining a queue of the processes in the main memory, and one of the process from the ready state will be scheduled at the CPU, and when a process comes to the CPU for the execution, we say that the process is in the run state. So, from ready to run state. When the process completes its execution, we say that the process is there in the terminated state or the termination state. During the execution of the process may require some input output, means it may require the data or the instruction to be brought in from the hard disk, or it may require some output to be generated at the output device. So, these are called the input output operations. So, when a process requires the input output operations, we say that the process is there in the waiting state or the blocked state. When the IO operations completes, the process is brought from the waiting state to the ready state, and this cycle continues. So, ready, run, wait or block, then again ready, and then again run, and when the process has completed, let us go to the completion state. Let us say my memory is full, my main memory is packed, there is no space for bringing any other process in, but a high priority process wants to come in immediately. For bringing the high priority process in, we will be sending out one of the process from main memory out, creating the space, and then the high priority process can come into the ready state or the main memory. So, the process which is there in the main memory in the ready state is taken out from the main memory and sent to the hard disk, but temporarily it has been sent. That is why we are saying that the process is in the suspended state, suspended ready state. And when a process completes, when the high priority process which was brought in completes and the space is created in the main memory, this process can again resume in the ready state. So, the process is brought from ready state to the suspended ready in the hard disk, and then from suspended state it is brought or it is resumed to the ready state. After this, You can think of why to bring a process from the ready state, why not to bring a process from the waiting state, because waiting state process cannot be allocated to CPU immediately. So, let us block the process from the waiting state, so it becomes in the suspended wait state. So, the same procedure is applied whatever has happened in the suspended ready state, but the suspended wait means the process in the waiting state is taken out from the hard disk than the process which is there in the ready state. So, when the space is created, the suspended wait state is terminated and we bring the process to the suspended ready and finally to the ready state after the resumption. So, these are the process states that we have discussed. We need to create a data structure that keeps the information about all the processes in the system. So, for maintaining the information about all the processes in the system, we require a process control block. We say that this is PCB. It is a very important component of our process, of our programming system, wherein a process and its different states and the components of the process, meaning that whatever resources it has occupied, the record of all these things are stored in the process control block. So, let us look at what are the different components that we require a process control block to contain. So, the very first thing is the process state. We have seen that the process can remain in several states. So, what is the current state of the system that needs to be recorded and stored in the process control block? Then the program counter. Program counter tells us what is the next instruction to be executed. If we know that the next instruction to be executed has given some address in the main memory, so that address should be stored in some variable or some register that is known as the program counter. And then there are some process centric registers in our system. Whenever the process is running, so CPU registers store some information related to the process. So, what is the state or what are the values of those registers, or what are those registers which are containing the value related to the process, that is stored also there in the PCB, process control block. Then the CPU scheduling information means what is the priority of the process, okay? Where is the scheduling queue, the pointer to the scheduling queue. So, that is also stored in the CPU scheduling information there in the PCB or the process control block. Then the memory management information, for example, what is the location of the process in the main memory. So, the boundaries of the process should also be known. So, that also is stored in the PCB. During the execution of the process has elapsed some time for the execution and some time will be remaining for the execution of the process. So, we should know that how much time a process has already spent on the CPU, how much time it has spent for the IO operations, how much time it has elapsed from the start for the execution of the process. So, all these informations are stored as the accounting information in the PCB. And finally, when a process is running, it will be occupying or it will be taking hold of some resources. So, we should have the information of all those resources which are being used by our process, so that we can check about what the resource can be provided to the other processes which are attempting to execute in the system. So, list of all the input output devices which are open, and similarly a process while the execution may require some files to work with. So, the information about all those files are also stored there in the PCB. So, the PCB stores several informations related to the process, and the very important thing which is left out here is the process ID. We allocate some ID to the process. It may be numeric number or it may be something else, but we allocate some ID to the process. So, this process ID is also stored in the PCB. This is the unique identifier for the process. Now, all the things that we have stated earlier is mentioned here in this table. This is the PCB, we can say that this is the PCB for one process. So, this PCB is storing process state, obviously the process ID, we should not forget this, process ID, process state, process number, program counter, register, memory limits, list of open files and list of open devices. Now, when we are working in the system, several processes must be running. When the several processes are running, we should maintain the record of all the PCBs, and usually the PCBs are stored in the form of the linked list. A diagram given below suggests you that there is a PCB of process number 1, there is a PCB of process number 2 that is linked with process number 1, then PCB of 3 is linked with process number 2, and so on and so forth. If we have n processes, the last node is suggesting you the process control block of the last process. So, we are storing all these information or all these PCBs in the form of the linked list. Now, when a process switches from when the CPU switches from one process to the other, so this timing diagram must be telling you that what happens in between. This is with respect to the process control block. So, there is one process which is executing, let us say the P0 process, and P0 process is terminated, or sorry, the P0 process is interrupted by some other process. So, when P0 process is interrupted, we will be saving the state of P0 in the PCB, and then we will be loading the next process which is to be executed at the CPU. So, we should load the PCB of process number 1, let us say the next process which is to be executed is process number 1. So, PCB of second process is loaded, and then P1 process executes. When the P1 process completes the execution, we save the state of P1 process in the PCB of one process or process number 1, and then we reload the state of the PCB 0, it means we reload the process P0. So, everything is done with the help of the PCBs. When the P0 was interrupted and when the P0 is brought back, the time in between these two is idle, this P0 process has done nothing in between. Now, when let us refer to the previous diagram only, a P0 process is currently executing, it is preempted, it is interrupted to bring the process P1 in. It means that to interrupt the process P0, all the state or all the information related to the P0 should be stored in the PCB, and then for bringing the process P1 for the execution, we should load the PCB of process number 1 in the main memory or for the execution. So, we are actually shifting from the context of P0 to the context of P1, or the state of P0 process is saved and the state of other process is brought for the execution. In fact, we are doing the context switching. So, context of a process represents is represented in the PCB. What is the context? Context is the information related to the process, information related to the current state of the process. So, when P0 is interrupted, we are saving the context of P0, and then we are reloading the context of P1 process. So, it is the context switch, we are switching from the context of one process to the context of the other process. So, this is known as the context switching. So, when CPU switches to another process, the OS must save the state of currently running process and load the saved state of new process via a context switch. Now, there are several queues maintained in the system. Queues means there are several aspirants for main memory, several aspirants for CPU execution, several aspirants for doing the IO operations. When we are dealing with the multiple processes, if you press Alt Control Del in your system and see the processes which are running, you will find that hundreds of the processes are running at the same time. So, we cannot give all the resources to all the processes at the same time. So, what we do that we maintain a queue, we maintain a buffer, so that from that buffer only we select a process either for the CPU execution or for providing the input output or for bringing those processes which are interested in coming in. So, there are 3 queues. Let us start with the ready queue. Ready queue means all those processes which are intended to use the CPU are there in the ready queue. So, whenever we are submitting a process in the system, obviously they will be using the CPU. So, they will be in the ready queue. So, one of the process from the ready queue is taken and that is scheduled at the CPU. So, ready queue is maintaining the processes which are residing in main memory and ready for execution at the CPU. Now, the device queue. Device queue is a queue of all those processes which require the input output. So, all those processes which are requiring the input output, they should be there in the device queue. We cannot allocate the input output device to all the processes which require the input output at the moment. So, we should maintain the list of all those processes in the form of a buffer, and we should pick one process from there for performing the input output at a time. And then there may be all the processes in the system which are there in the ready queue or the device queue or somewhere else. We maintain the record of all those in the job queue. So, all those jobs or all those processes which are there in the system, that may be there in the ready queue or that may be there in the device queue or maybe in some other places, we actually maintain their record in the job queue. So, these are the 3 types of queue that the operating system maintains. Now, you can see that there is a diagram of the ready queue here. A process has been submitted to the ready queue. The process from the ready queue is taken and this is allocated at the CPU. Now, this process, when it was executing at the CPU, gives a IO request. So, it is taken out of the CPU and it is entering the IO queue, and after the completion of the IO, it again comes back to the ready queue. Okay. Let us say we are dealing with the round robin manner and some time quantum is assigned for the execution of a process. It cannot go more than 4 unit of time, or it cannot execute for more than 4 unit of time. So, when the 4 unit completes, the process will be preempted from the CPU, process will be taken out from the CPU and we will bring it to the ready state. Okay. When we are creating the child process with the help of the fork, after the creation of the child process, this process needs to come in the ready queue. When a process is waiting for some interrupt to occur, when the interrupt has occurred, we take the action as per the interrupt and bring this process in the ready state, so that in the next cycle it can be given the CPU. Now, there are some types of the schedulers in the system. Schedulers means from the queues we have to decide which process to take in. So, there are 3 types of schedulers basically. One is the short term scheduler that will be deciding which process to be given the CPU. There is a long term scheduler which decides that which process will come into the main memory, because a process will be coming into the main memory for a very long time. It will be doing some CPU executions, it will be doing some IO operations. So, altogether it will be spending lot of time in the system. Since it will be spending lot of time in the system, it will be called the long term scheduler that will schedule these processes in the system. So, long term scheduler should be controlling the degree of the multiprogramming, that how many processes can come in. And finally, the medium term scheduler. With the help of the state transition diagram, I told you that there are some processes which may be suspended temporarily for bringing the high priority process in. So, which is that process that should come in? So, this decision has to be taken by the medium term scheduler. So, these are the intelligent schedulers are actually the intelligent programs that decide that which process should be sent to the CPU. So, the short term scheduler, which process should come into the main memory, long term scheduler, which process should be taken out from the main memory and suspended temporarily, will be decided by the medium term schedulers. Now, there are two types of the processes usually, IO bound processes and the CPU bound processes. The IO bound processes spend more time for the IO operations and very less time for at the CPU. So, most of the time of the execution of the IO bound processes goes for the input output and very less time is allocated at the CPU. The CPU bound processes spend more time at the CPU and very less time for the IO operations. For example, the system processes are usually the CPU bound processes. So, the long term scheduler has to create a balance between the two types of the processes, IO bound processes and the CPU bound processes. Since the RAM is limited, hence the responsibility of the long term scheduler is to create a balance between the two types of processes such that there is no starvation for the other type of process. For example, if more number of IO bound processes have come into the system, so the CPU bound processes will be starved, and when the CPU bound processes have been brought in, then the IO bound processes will starve. So, a balance should be created by the long term schedulers, so that no other process is starved or no other type of the process is starved. Now, who does the CPU? We are dealing with the CPU scheduling now. CPU scheduling means the process has to be allocated to the CPU. So, obviously, this will be brought from the ready queue for coming in. So, who should decide this? The short term scheduler. The short term scheduler will decide that which process will come in and where it has to come from ready state to the running state. When it has to come? When a process moves from run to the termination, means a process has completed, the new process should come in. When a process is going from run to wait, a process requires input output operation. So, it is freeing the CPU. So, CPU can execute another job. So, the CPU the short term scheduler should bring in one process from the ready state to the run state. When we are saying that a process is running using the round robin scheduling, it is executing the process for short amount of time and then it will be taken back, or when a process is dealing with something and some interrupt occurs, in that case the process will be sent from run state to the ready state. So, in both the cases the process will or the short term scheduler will decide that which process is required to be executed at the CPU. So, a process will be brought from the ready state to the run state for the execution. Fine. Now, these are the CPU scheduling criteria. Whenever we are dealing with the CPU scheduling, we must have the awareness about the arrival time, burst time, turnaround time, waiting time and response time. The arrival time is the time at which a process is arriving in the ready queue. Burst time is the amount of time a process requires for the CPU execution. Turnaround time is the amount of time a process spends in the system completely. For example, a process has come in and the process is completed. If the time at which the process has come in x and when the process has exited is y, then y minus x is representing the turnaround time. Then the waiting time is the wastage of time, or you can say that the amount of time a process is not executing the CPU is the waiting time. So, let us say a z amount of time is required for a process to execute at the CPU and y minus x is representing the turnaround time. So, rest of the time this process must have waited. So, y minus x, which is the turnaround time, minus z, which is the execution time or the burst time of a process, is the waiting time. Now, the response time means the process, what is the time at which the process gets the CPU for the first time in the first time for the execution. Now, these are the different scheduling algorithms that we will discuss in the next turns. The scheduling criteria would be to minimize the response time, to increase the throughput means the maximum number of processes should execute in the minimum amount of time, and to minimize the waiting time. This is the reference for this lecture. Thank you.